Hi class, here's some more problems on exponential growth and exponential decay. With this one, HTI bought a computer for $2,500 and it's expected to depreciate at a rate of 20% per year. What will the value of the computer be in 2 years? So this is an exponential decay problem. We're going down in value. Our equation is still y equals AR raised to the t. So what will the value of the computer be worth in 2 years? We want to know what y is. So y equals, the initial amount is letter A, so the initial amount of the computer is 2,500, multiplied by the rate. Now it's expected to depreciate at a rate of 20%. So just like class on exponential growth problems, we always added the percent to 100. On this one, we're going to subtract the percent from 100. The reason for that is if we subtract 20%, it still retains 80% of its value, and that R value, that rate, is the amount of increase, the rate of increase. So it's depreciating at a rate of 20%. So that means it's retaining 80% of its value. So that's why it's very important to always add to 100 if it's exponential growth, or subtract from 100 when it's exponential decay. So there it's retaining 80%, so as a decimal, we're going to put 0.8 in there for the rate. And that's raised to the time t, and the time t in this one is going to be in 2 years. There's our time t. Once again, this one's pretty basic. All you got to do is put this in your calculator now. Make sure you do exponents first. So 0.8 times 0.8, whatever that number is, multiplied by 2,500. So y equals, that computer is worth $1,600 after 2 years. $1,600. There's number 4. Looking at number 5, a cup of coffee contains 130 milligrams of caffeine. If the caffeine is eliminated from the body at a rate of 11% per hour, how long will it take for 90% of the caffeine to be eliminated from the person's body? So once again, it's going to be an exponential decay problem because the amount of caffeine is decreasing. So we're still going to use y equals AR raised to the t. A is the initial value, so we started off with 130 milligrams. The rate, it's eliminated from the body at 11% per hour. So just like on our last one, when it's exponential decay, you subtract the percent from 100. So that means it's 89%. As a decimal, 0.89. Raised to the t, and our t is going to be our variable. How long will it take? What's our time t? That's what we want to know. So now the question is what is my ending amount? What's this value right here? What is the y after time t? Well, we want to know how long will it take for 90% of this caffeine to be eliminated from the person's body. So if we start off at 130, we want 90 of it to be eliminated. So what is 130 multiplied by 0.9? 130 times 0.9 is 117. So when will 117 grams be eliminated from the body? So if it's 117 grams that's gone, how much is remaining? If we take, starting off at 130 milligrams, and then we got rid of 90%, so 117, how much is left remaining? 130 minus 117 is 13 grams. So that is my amount at time t. How long will it take for 90% of this caffeine to be eliminated? Well, if 90% is eliminated, that means 13 milligrams are left. So now here is our equation, and now we're going to solve for time t. Very first thing, let's now divide by 130. And if you take 13 divided by 130, you get 0.1. That equals 0.89 raised to the t. Whenever you have an exponent as a variable, you're going to solve that for that exponent using logs. So we're going to take the log of both sides, log of 0.1, that equals the log of 0.89 raised to the t, but the t can come out front as a coefficient again. So what is t? Divide both sides by the log of 0.89. Divide by the log of 0.89. Do that in your calculator and that will get you the answer. The log of 0.1 divided by the log of 0.89, and you will get approximately 19.7589 hours. T is approximately equal to 19.7589 hours. So on a test class, I'm fine if you round this up after about 20 hours. 90% of the caffeine. How do you spell caffeine? That wasn't right. There we are. Is eliminated from the body. Let me know if you have any questions on that when you get to class tomorrow.